Okay, hello guys, welcome to Crown Smart. In this video we're going to still deal with another example of topological space, which is the discrete topological space. Now here says that show that tau is a topology on X where this is the power set, tau is the power set, and is defined as the collection of A such that A is a subset of X. Now recall that our power set is the set that contains all subsets of X. Let's example, we have a set, let's say X is AB. Okay, let's use AB just to save time. Now the power set of X is just the collection of the empty set, which is a subset of this, because empty set is a subset of every set including itself. We have the set itself, it's a subset of itself. We also have the singleton A, and we also have the singleton B. Now this is actually the power set of this set X. Okay, so it's the collection of all the subsets of this set X. So this is just an example, an idea of what a power set is. Now, X is an arbitrary set and X is non-empty. Please take note where X is non-empty. Where X is not empty at this point. We don't want X to be empty. So X is an arbitrary set and we don't want X to be empty actually. So we want to show that the power sets, we want to show that this where the topology is equal to the power set, we want to show that this is a topological space. That is, we want to show that X, P of X is a topological space. Okay, now for us to show that this is a topological space, then we must show that it satisfies the following three axioms. Okay, the first axiom is that the empty and the whole set must be in the topology. The arbitrary union in the topology must be in the topology, and the finite intersection of open set in the topology must also be in the topology. So now solution, or should I say proof, right? Okay, solution or proof anyway. So we have that. Okay, we know that the empty set is a subset of X. We know that the empty set is the subset of X. Therefore, okay, this implies that the empty set is in what? Is in P of X, and this is true. Since the empty set is a subset of X, this implies that the empty set is in P of X. Remember, we said that the empty set is always a subset of any set. No matter the set given, the empty set is always a subset of any set. So since the empty set is a subset of X, this implies that the empty set is in P of X. Okay, we also have that the set itself is a subset of itself, right? So this implies that the set is in what? P of X. Remember this condition, that P of this is a collection of A such that A is a subset of X. So if A is a subset of X, then this means that A must be in what? P of X. So we're using the ideology here that since X is a subset of X, therefore X is in what? P of X. So we are giving a conclusion that X is in P of X since X is a subset of itself. So we have satisfied the first axiom. Now the second axiom. Now we now say, okay, take any collection of open sets, that is, let's say collection of, let me not use O, let me use A alpha, such that alpha is in delta, where A alpha is in the topology for each alpha in delta. For each alpha in the index set, this delta represents the index set. So take any collection of open sets, that is the collection this where alpha is in the topology for each alpha in delta. Then since A alpha is in the topology, what does this mean? That A alpha is a subset of what? X. Remember, A is in this topology, therefore A is a subset of what? X. A is in this topology with the condition that A is a subset of X. So if A alpha is in this topology, then it means that A alpha has a condition that it is a subset of what? X. And because it's a subset of X, this implies that the union of A alpha as alpha goes with index is also a subset of what? X. Now some of you may be confused why I said the union of this will also be a subset of X. If A alpha is a subset of X, then the union of this is a subset of X. Now take it as if I said, okay, just let me make it more understandable. Let's say we have that A alpha is a subset of X. I can say, okay, take the union of both sides, that is the union of A alpha as alpha in delta be a subset of the union of X. Okay, this is just a rough part. Now we know that the union of this will also be a subset of the union of this, since this is a subset of this, right? So what's the union of X is X, right? So the union of this will be a subset of what? X, since the union of X is already what? X. Now if the union of A alpha as we pick alpha from delta is a subset of X, what does this imply? This also implies that the union of A alpha as alpha from the index set will always be in what? The topology, since A is open set such that A is a subset of X. So if this is a subset of X, therefore this must be in the what? The topology. So we are using the conditions to solve the problem. So we said take any collection of open sets, that is, this is the collection where A alpha is in this for each alpha in the delta. Then A alpha is a subset of X. Now because A alpha is a subset of X, this implies that its union is a subset of X. Now A alpha is a subset of X because A alpha is in this. Because A alpha is in this topology means that A alpha will be a subset of X. Now since A alpha is a subset of X, then its union will be a subset of what? X. And since its union is a subset of X, this also implies that this union will be in the what? In the topology. So we move over to the third part. Take any what? Finite collection. Take any finite collection. Sorry, in this part we're supposed to say take any arbitrary, please forgive me, take any arbitrary collection of open sets, please take any arbitrary collection. So here we are taking any finite collection of open sets, that is this collection of AI such that I is equal to 1 to n, where AI is in the topology for each I equal to 1 to to n. Now take any finite collection of open sets, that is this, you're taking this where this ai is in the topology for each I in this. Now since ai is in this topology, what does it imply? If ai is in this topology, it means that ai is a subset of what? X. So this means that then let me put it this way. Since ai is in J, then ai is a subset of what? X for each I equal to 1 to n. Now since ai also is a subset of X, what does this also imply? This also implies that ai is a subset of X. Now if ai is a subset of X, this implies that the finite union of ai equal to 1 to n will also be a subset of what? Of X. That the finite union of this ai will also be a subset of X. Okay, and since the finite union of this is also a subset of X, this implies that the finite union I equal to 1 to n will be in what? A topology. Because from our definition of topology, for anything to be a subset of X, therefore that thing is in the what? A topology. But here we have that the finite union of ai is a subset of X. Remember, when something is a subset of X, then its union is a subset of X. So its finite union is a subset of X, meaning that from our definition that this finite union will be in the what? In the topology. Hence, this is a topology on what? S. So therefore the discrete topology is a topology on X. Okay, so that's the end of our proof. I hope you enjoyed this video. Please do not forget to subscribe. Very, very important. With by subscribing, you are actually giving us the impression to do more videos. Please do not forget to subscribe, and we'll try our best to make this video very easy for you guys. Thank you very much.